A half adder adds two single-bit binary numbers A and B. The only possible input combinations are 0, 0, 0, 1, 1, 0, and 1, 1. The sum S is the least significant bit of the result, while the carry C is the bit that is passed to the next higher position. A B yields SC0, 0 yields 0, 0. 0, 1 yields 1, 0. 1, 0 yields 1, 0. 1, 1 yields 0, 1. Sum S equals A exclusive or B exclusive, or this is true when exactly one of A or B is 1. Carry C equals A and B, and the carry is produced only when both inputs are 1. These compact equations are the basis for every larger adder design. The exclusive or can also be expressed with basic gates. S equals A and not B, or not A and B. The and for carry is already minimal. Think of A and B as two people each holding a single coin. The sum tells you whether the total number of coins is odd. One person has a coin, like a light that turns on if exactly one coin is present. The carry tells you whether both have a coin, so you need to pass one coin to the next hand, next bit. The half adder can be built directly with the two gates identified above. XOR gate for the sum, a ND gate for the carry. The circuit symbol looks like a small box with two inputs A, B, and two outputs S, C. NAND only implementation. Because NAND is a universal gate, we can recreate XOR and a ND using only NANDS. 1. A ND using NAND. A dot B equals not a NAND B. 2. NANDS first produces NAND, second inverts. 2. XOR using NAND. X1 equals a NAND B. X2 equals a NAND X1. X3 equals B NAND X1. S equals X2 NAND X3. 4 NAND gates total. Thus, the half adder needs 6 NAND gates, 2 for carry, 4 for sum. NOR only implementation follows the same idea because NOR is also universal. 1. OR using NOR. A plus B equals not at NOR not B. 2. As ND using NOR. A dot B equals not at NOR not B, and OR not at NOR not B. 3. NORS. 3. XOR using NOR can be derived as N1 equals at NORB, N2 equals at NORN1, N3 equals BNORN1, S equals N2 NORN3. 4 NOR gates. Overall 7 NOR gates are required, 3 for carry, 4 for sum. Real-world view: imagine you only have a certain brand of tool, say only hammers. Even though a screwdriver would be ideal, you can still build a functional door handle by creatively using hammers and nails. NAND/NOR only adders are the same idea in digital hardware. A full adder adds 3 1-bit numbers, the 2 operand bits A and B plus an incoming carry in SIN. The outputs are sum S and carry out count. A B SIN produces S and count. 0 0 0 gives 0 0, 0 0 1 gives 1 0, 0 1 0 gives 1 0, 0 1 1 gives 0 1, 1 0 0 gives 1 0, 1 0 1 gives 0 1, 1 1 0 gives 0 1, 1 1 1 gives 1 1. From the table we can derive the Boolean functions. Sum S equals a XOR B XOR SIN. This is a 3-input XOR, true when an odd number of inputs are 1. Carry out count equals A and B plus B and SIN plus A and SIN. This is the majority function. It is 1 when at least 2 of the 3 inputs are 1. Both expressions are already minimized. The sum cannot be reduced further without using XOR as a primitive, and the carry expression is a sum of products with 3 product terms, each having 2 literals. Analogy: picture 3 people each holding a coin, A, B, SIN. The sum tells you whether the total number of coins is odd, light on. The carry out tells you whether at least 2 people have a coin, meaning 1 coin must be handed to the next column. Explanation: the textbook way to build a full adder is to reuse the half adder building block. First half adder adds A and B producing. Intermediate sum equals S1 equals a XOR B. Intermediate carry equals C1 equals A and B. Second half adder adds S1 and SIN giving. Final sum equals S1 XOR SIN, which is a XOR B XOR SIN. Second carry equals C2 equals S1 and SIN. The 2 carry outputs are combined with an OR gate. C out equals C1 plus C2 equals A and B plus a XOR B and SIN. Using the identity A XOR B and SIN equals A and SIN plus B and SIN, The result matches the minimized expression derived earlier. The schematic consists of 2 XORs, 2 ANDs, and 1 OR, 6 basic gates. Practical view: this modular approach is like building a larger Lego structure by first making 2 smaller sub-assemblies, half adders, and then snapping them together with a single connector or gate. It simplifies design, testing, and reuse. Explanation: because NAND and NOR by themselves can implement any Boolean function, a full adder can be realized without any other gate type. The goal is to keep the gate count low because each gate adds area and delay. NAND only full adder, 8 NAND gates is common optimum. 1. Generate the 3 2-input AND terms for the carry using NAND, then invert technique. N1 equals a NANDB. Yield C1 equals not N1, second NAND with tied inputs. N2 equals a NAND sin. Yield C2 equals not N2. N3 equals B NAND sin. Yield C3 equals not N3. 2. Combine the 3 carries with a NAND-based OR De Morgan. Not open parenthesis, not C1 and not C2 and not C3 close parenthesis. Implement as NAND of the 3 inverted carries. This needs one more NAND that feeds the 3 previous outputs. 3. For the sum 3 input exclusive OR, we can use the known 4 NAND exclusive OR block twice. First exclusive OR, S1 equals an exclusive ORB 4 NANDS. Second exclusive OR, S equals S1 exclusive OR sin, another 4 NANDS. Total equals 4 plus 4 plus 4. Carry network equals 12 NANDS. But by sharing some inversions, the count can be reduced to 8 to 9 NAND gates. Many textbooks present an 8 NAND solution that reuses the NAND that already produces not open parenthesis A and B close parenthesis. NOR only full adder is symmetric. Use a 4 NOR exclusive OR, 3 2-input NOR based ANDs, and 1 NOR to OR the carries. An efficient implementation also reaches 8 NOR gates. Why optimize gate count? In silicon, each gate consumes transistors, power, and adds propagation delay. Fewer gates equals smaller chip, lower power, faster operation, critical for high-speed processors. Explanation: to add numbers wider than 1 bit, we chain full adders so that the carry out of the less significant stage becomes the carry in of the next stage. This is called a ripple carry adder RCA because the carry ripples through the chain. If we have n bits, the RCA consists of n full adder cells named FA0 to FAN-1. Inputs AI BI with I equals 0 to n-1 and an initial carry in C0, often 0. Outputs SI sum bits and final carry out CN. Boolean description for each stage ISI equals a ISOR B ISOR C ICI is the carry in for stage ICI plus 1 equals AI and BI plus BI and CI plus AI and CI. Putting all stages together yields the overall function. S0 to Sn-1 and Cn equals sum from I equals 0 to n-1 of AI plus 2 times BI plus C0 base 2 addition. In hardware description language HDL, it looks like a sign Cn and Sn-1 to 0 equals a plus B plus C. 0 synthesizer will infer an RCA or a faster adder. Real-world picture. Imagine a line of people passing a bucket of water carry. The first person fills his cup some, and if the bucket overflows, passes the excess to the next person. The overflow travels down the line until no one needs to pass it further. Explanation: the speed of an RCA is limited by the time it takes for a carry to travel from the least significant stage to the most significant stage. Propagation delay, TP of a gate, is the time from a change at its input to a stable change at its output. For a full adder, the critical path is through the carry logic because the sum depends on the incoming carry. Carry propagation delay for one stage approximately TP of carry logic. If we denote the delay of a single full adder's carry path as TFA, then for an n-bit ripple carry adder the worst case delay is T worst equals n times TFA, carry must ripple through all n stages. If the sum output uses an XOR that also depends on the carry, the sum delay adds a small extra term TXOR, but this is usually much smaller than the ripple delay. Practical numbers. In a 45-nanometer CMOS library, a typical full adder carry path may be approximately 30 picoseconds. For a 32-bit RCA, the worst case approximately 960 picoseconds, which is often too slow for high-performance CPUs. Therefore, designers use faster adders, carry lookahead, carry select, etc. Impact of gate count. More gates in a stage increase TFA, while using NAND or NOR-only implementations can modestly increase delay because extra inversions are needed. Analogy: think of a line of dominoes. Tipping the first domino, least significant carry, starts a chain reaction. The time for the last domino to fall grows linearly with the number of dominoes, exactly how ripple carry delay grows with bit width. Inputs 2 bits A and B versus 3 bits A, B and sin. Outputs sum and carry versus sum and cout. Boolean size: sum equals exclusive or 2 input, carry equals and 2 input versus sum equals 3 input exclusive or, carry equals 3 2 input and terms plus or. Gate count: basic gates. 1 exclusive or plus 1 and equals 2 gates versus 2 exclusive or plus 2 and plus 1 or equals 5 gates, or 2 half adders plus or equals 5. NAND only gates: 6 NANDs typical versus 8 to 9 NANDs optimized. Typical use: building blocks for larger adders, simple parity generators, low-bit arithmetic versus core of multi-bit adders, ripple carry, carry lookahead, ALU arithmetic units. Practical example: adding 2 1-bit flags overflow detection versus adding 2 8-bit numbers in a microcontroller ALU. Why full adder matters. A half adder cannot handle a carry that arrives from a lower order addition. In any real-world binary addition more than 1 bit, the carry-in must be accounted for, which is exactly what a full adder does. Using half adders only would require extra logic to feed the carry back, making the circuit larger and slower. Full adders give a clean uniform cell that can be tiled, simplifying layout and timing closure. Real-world analogy: a half adder is like a single-lane bridge that can only let 2 cars cross at a time. A full adder is a 2-lane bridge that also allows a car coming from an upstream lane carry in to join the crossing, keeping traffic flowing. Problem 1 - derive the sum and carry expressions. Given inputs A, B, C, and write the Boolean equations for the sum S and carry out cout. A solution: sum equals S equals a XOR B XOR C in equals open parenthesis A and not B and not C in close parenthesis, plus open parenthesis not A and B and not C in close parenthesis, plus open parenthesis not A and not B and C close parenthesis, plus open parenthesis A and B and C close parenthesis. Carry out cout equals open parenthesis A and B close parenthesis plus open parenthesis B and C in close parenthesis, plus open parenthesis A and C in close parenthesis. Problem 2 - design a NAND-only full adder. Using only 2 input NAND gates, draw the schematic that implements the full adder with the minimum number of NANDs. Hint: use the 4 NAND XOR block twice for the sum, and reuse the NAND that generates not open parenthesis A and B close parenthesis for the carry network. Answer sketch: gate count equals 8 NANDs. Step 1: N1 equals a NAND B, yield C1 equals N1 NAND N1. Step 2: N2 equals a NAND Cin, yield C2 equals N2 NAND N2. Step 3: N3 equals B NAND Cin, yield C3 equals N3 NAND N3. Step 4: Carry OR. Cout equals open parenthesis C1 NAND C2 close parenthesis NAND, open parenthesis C1 NAND C3 close parenthesis NAND, open parenthesis C2 NAND C3 close parenthesis. Simplified to 2 more NANDs. Step 5: XOR1 a XOR B uses N4 through N7. Step 6: XOR2, XOR1 XOR Cin uses N8 through N11. Reusing some inverted signals reduces count to 8 total. Problem 3 - worst case delay of a 4-bit ripple carry adder. Assume each full adder's carry path delay TFA equals 35 picoseconds, and the sum path adds an extra 10 picoseconds after the carry is received. Compute the maximum propagation time from the least significant carry in to the most significant sum output. A solution: carry must ripple through 4 stages. 4 times 35 picoseconds equals 140 picoseconds. After the final carry arrives, the most significant sum needs the extra 10 picoseconds. total worst-case delay equals 140 picoseconds plus 10 picoseconds equals 150 picoseconds. These exercises test the ability to translate truth tables into equations, to apply universal gate synthesis, and to perform timing analysis, all core skills for digital design courses. Tip for students: when drawing NAND-only circuits, first write the desired expression, then replace every AND with NAND followed by NAND, which provides inversion, every OR with NAND of inverted inputs according to De Morgan, and every NOT with a NAND tied together. This systematic method prevents missing a gate.